Hi everyone. Today I will be presenting Module 4, that is Magnetic Materials and Devices, from our Physics for Computer Technology course. In this session, we will explore the origin of magnetism, how materials are classified based on their magnetic properties, the concept of magnetic domains, and the practical applications of these materials in technology. Here is an overview of what we will be covering today. We will start with the origin of magnetic moments in atoms. Then we will move on to the classification of magnetic materials such as diamagnetic, paramagnetic, and ferromagnetic substances. Next, we will discuss the domain theory, which explains why ferromagnetic materials show strong magnetism. After that, I will explain the process of domain magnetization, and finally we will see the different types of energies involved in domain growth. So let's begin with the basics. What is magnetic materials? Magnetic materials are substances that can be magnetized when we apply an external magnetic field. Some materials have a, a natural or permanent magnetic moment, while others develop one only when exposed to a field. For example, iron, cobalt, and nickel are well-known magnetic materials that can easily be magnetized. On the other hand, materials like copper, brass, or aluminum are not magnetic. The essential difference lies in the way electrons are arranged inside the atoms of these materials. Now let us see the origin of magnetic moment. Now let's look at the origin of magnetic moment. Inside an atom, electrons move in two ways. We know that they spin around their own axis and they revolve around the nucleus in orbits. Both of these motions create tiny magnetic fields. The magnetic effect due to electron spin is called the spin magnetic moment, and the effect due to orbital motion is called the orbital magnetic moment. When we add up these contributions, we get the total magnetic moment of an atom. The smallest unit of magnetic moment is called the Bohr magnetron, which is equal to 9.27 into 10 power minus 24 ampere meter. And then, the magnetic behavior of any material ultimately comes from the motion and spin of its electrons. Now let us see the applications of magnetic materials. Magnetic materials play a vital role in our daily life and technology. They are used in data storage devices like hard disk, magnetic tapes, and credit cards. In the power sector, soft magnetic materials are essential in transformers, inductors, and generators. Permanent magnets are used in motors, loudspeakers, and sensors. In modern computing, magnetic materials from the basics of magnetic memory and spintronic devices, where the electron spin is used for data processing. So the study of these materials is not just theoretical, but has wide-ranging practical importance. Before we classify magnetic materials, let us go through some basic definitions. A magnetic dipole is simply two poles, north and south, separated by a distance, is known as the magnetic dipole. The magnetic dipole moment is the strength of the pole multiplied by this separation. So magnetic induction, represented as B, is the measure of internal field within a material. Magnetic field intensity, represented as H, is the strength of external field applied. Permeability tells us how easily a material can be magnetized, and susceptibility measures how much magnetization is produced per unit applied field. So these definitions will help us clearly understand the different types of magnetic materials. Now, let us see the classification of magnetic material. Magnetic materials are generally classified into two broad categories. The first group consists of materials that do not have permanent magnetic moment, such as diamagnetic materials. The second group includes those with a permanent magnetic moment, which are further divided into paramagnetic, ferromagnetic, antiferromagnetic, and ferrimagnetic materials. Each of these groups behaves differently when placed in a magnetic field. Let's compare three major types: diamagnetic, paramagnetic, and ferromagnetic materials. Diamagnetic materials have all their electrons paired, so the spin cancel each other. They show very weak negative magnetism and are repelled by a field. Their susceptibility is negative and the permeability is slightly less than 1. Example include copper, bismuth and silver. When coming to the paramagnetic material, it has some unpaired electron. So they develop a small positive magnetization when placed in a field. Their susceptibility is positive but small and permeability is slight greater than 1. Examples are aluminum and platinum. When coming to the ferromagnetic materials like iron, cobalt and nickel have large number of unpaired electrons. Their atomic movements align in the same direction, producing strong magnetism. They have very high permeability and large positive susceptibility. It is also important to note the effect of temperature. For instance, when a ferromagnetic material is heated above certain temperature, called the Curie temperature, it loses its ferromagnetism and becomes paramagnetic. Similarly, if the temperature is less than critical temperature, paramagnetic material is become diamagnetic material, and temperature is greater than critical temperature, ferromagnetic material become paramagnetic material. This is about the classification of magnetic material. Now let us see the domain theory. So which explains why ferromagnetic materials are so strongly magnetic. A ferromagnetic material, here we can see in this picture, a ferromagnetic material is divided into small regions called domains. Within each domain, the atomic magnetic moments are aligned in the same direction. So the domain has strong magnetization. However, uh, in an unmagnetized sample, these domains are oriented randomly and the net magnetization is zero. When we apply a magnetic field, the domains begin to align with the field and the material becomes strongly magnetized. This theory was proposed to explain the very large magnetic susceptibility of ferromagnetic substances. Now let us see the process of domain magnetization. The magnetization process occurs in two stages. One is domain wall movement and another one is domain rotation. At low field strength, when small amount of magnetic field is applied, the domains that are already aligned with the field grow in size by moving the boundaries or domain walls. And then domain rotation at the higher field strength. If you are applying the higher magnetic field, entire domains rotate so that their magnetization aligns with the applied field. These uh, two-step process explains why ferromagnetic materials can be magnetized so easily and strongly. When we applying the small magnetic field, small external magnetic field, the magnetization occurs very low. But when applying the strong magnetic field, the magnetization occurs very high. So this is the process of domain magnetization. And next, let us see types of energies involved in the domain growth. Let us look at the different types of energies involved in the domain growth. Exchange energy, crystalline anisotropic energy, domain wall or Black wall energy, magnetosection energy. Exchange energy is the energy that favors the parallel alignment of spins. Crystalline anisotropic energy arises because certain direction in crystal are energetically more favorable for magnetization. Domain wall or Black wall energy is the energy needed to form and maintain the boundaries between the domain. Magnetosection energy comes from the slight change in shape or strain of a material when it is magnetized. The balance between these energies determines how easily a material can be magnetized and how stable the magnetization will be. So in this video lecture, we learned that magnetic moment originates from electron spin and orbital motion. We classified materials into dia, para, ferro, and antiferro and ferri magnetic types. We explored the domain theory and the magnetization process, and we understood the different energies involved in the domain growth. Magnetic materials are fundamental in power systems, electronics, data storage, and modern computing. That brings us to the end of this session. Thank you for your kind attention for watching this video. In the coming videos, I will I will explain the hysteresis is involved in the domain growth that will be explained in the further videos. Thank you for watching this video. Thank you.